Number 49. So we have f of x is x cubed minus 2x squared plus x minus 1. Alright. So positive to negative, that's one variation. Check. Negative to positive, another variation. Check. Positive to negative, another variation of sign. Check. Alright. So for f of x we have three variations of sign, so that means that the number of positive real zeros is 3, or less than 3 by 2, 4, 6, and so on. Alright? So less than 3 by 2. In other words, 3 minus 2 is 1. So we either have 3 or 1 positive real zeros. What's f of negative x? So that's negative x cubed minus 2 negative x squared plus negative x minus 1. Alright? Now, negative x cubed is still negative x cubed. Alright? Negative 1 to the third power is, you write that as negative 1 times x. Negative 1 to the third is still negative 1. So it's still a negative. This becomes positive x squared, so it's minus 2x squared. And that becomes a minus, plus a minus is minus x minus 1. Alright? So how many variations of sign do we have? Negative to negative? No. Negative to negative? No. Negative to negative? No. So there are no variations of signs for f of negative x. So that means there are no negative real zeros. Negative real zeros. 0. Alright? So, total number of zeros, we can make a table again. I'll just put TOT for total. And positive reals, or just positive. Negative reals, or negative. And I'll put non for non-reals. Alright, so it's a degree 3, so there are 3 total roots. Okay, so we could have 3 positive real roots. Alright, that takes care of the total number. Okay, so that means that would be there would be no negative roots and no non-real roots. Again, total of 3. We could have 1 positive real root. Alright, so we could have, well, could we have 1 negative real? No, we already said there are no real roots, for negative real roots that is, so that has to be a 0 for both cases. So that means there would have to be 2 non-real roots to add up to 3, 2 plus 1. Okay, so if this were the case, you would see the graph crossing the x-axis only at one point on the positive side of the x-axis. You would not see these appear on the graph, okay, the non-real ones. Alright, so let's see what happens when we graph. And lo and behold, it only crosses the graph at one point, or the x-axis rather, at one point, and that's on the positive side. Alright, so it's got 1 positive real root and 2 non-real roots. Number 51. So if you look at the polynomial, there are no variations of sign for f of x, so there are no positive real zeros. What about f of negative x? So simplifying, we get negative 2x cubed plus 37x squared minus 200x plus 300. So from negative to positive, that's 1. Positive to negative is 2. And negative to positive is 3. So there are 3 variations of sign for f of negative x, and that means that the number of negative real zeros are 3 or 1. And there's going to be a total of 3 zeros because of the degree is 3. So let's make a little table. Total, we got 2 columns on this one. Since there are no real zeros, positive real zeros that is, and we've got, for negative real zeros, we've got 2 possibilities, 3 and 1. And non-real, so the 3 negative real zeros in this possibility will take up that total, so there would be no non-real zeros. In this possibility, you have 1 real, negative real, and that would leave 2 more. And there are no positive reals, so there must be 2 non-real zeros in this possibility. All right. So if we graph this, let's see what we have. And it turns out that the second case is correct, or the case. The second case is the one we're looking for. We've got 3 negative real zeros. As you can see, these 3 negative real zeros are to the left of the y-axis, and that's what we've got. Number 53. So let's take a look at this polynomial. We've got positive to negative, that's 1, change of sign. Negative to negative, nope. Negative to positive, that's 2. Positive to positive, no. So there are 2 variations or changes of sign in f of x. So that means there are either 2 or 0 positive real zeros. All right, 2 or 0. Now what about f of negative x? So we've got positive 2x to the 4th, and that negative is going to stay there, so that becomes positive 5x cubed minus 5x squared minus 5x plus 3. So positive to positive, that's nothing. Positive to negative is 1 change. Negative to negative is nothing. Negative to positive is 1 change. So that's 2 changes of sign in f of negative x. So that means there are 2 or 0 negative real zeros. Alright, so let's make a table. Total zeros would be 4 because of the degree, and there are going to be 4 columns here for 4 possibilities, 4 possible combinations of positive and negative real roots here. So for positive reals, 2, negative reals, let's say 2, and 2 plus 2 is 4, so that takes care of the total. So there would be no non-real roots in this column, this possibility set here. Alright, now let's say you have 2 positive reals, 0 negative reals. Alright, so that would mean there must be 2 non-real zeros to go along with those two positive ones. And let's say there are 0 positive real roots and 2 negative real roots, so that would leave you with 2 more non-real roots. And let's say there are 0 positive reals, 0 negative reals, so that would mean there are 4 non-real roots. Alright, so those are your possibilities. So let's look at the graph. And here it is. So as you can see, to the left of the y-axis we've got 2 negative real roots, and to the right we've got 2 positive real roots. Okay, so that first column in our table shows the actual situation. $55. So there are 2 variations of sign for f of x. So that means there are 2 or 0 positive real zeros. F of negative x is 10x to the 4th minus 21x squared plus 11. Same thing. So also there are 2 variations of sign there. So there are 2 or 0 negative real zeros. Now let's make a table. This table will be the same as our previous table in the last problem we did. So if you want to fast forward through this part, you'll know what's coming. We got 2, 2, 0, 0, negative real roots, 2, 0, 2, 0, and non-real zero, 2, 2, 4. Okay. Now, when you graph this, be careful. It does look on the graph, if you're using more or less the usual size of x and y axes, you know, a lot of people use from, oh, maybe -5 to 5, -5 to 5, going up and down. But if you do that, you're going to see on your grapher, especially given the resolution of your grapher or your computer, only 1 negative and 1 positive real root. In this case, you have to zoom in very tightly. Alright, so you'll see that the graph does dip slightly below the x-axis and intersects the x-axis more than once. Take a look. You've got to zoom right in on those points where the graph seems to just touch and bounce off the x-axis, and you'll notice that there are 4 real roots, 2 negative and 2 positive. All right, you'll notice the scale on the y-axis. It's pretty small. All right, 1/100th of a unit. All right, 1/100th is the scale on the y-axis. Each grid line, vertical grid line, represents 1/100th. All right, so that is something you'll just have to use your zoom feature on. All right. Now, before we leave this little section of the problems, maybe you were wondering if there are polynomials with real coefficients and a non-zero constant term with no real zeros. I don't think we've come across any like that yet. So let me give you one. So here's, call it P of X. I'll just draw a line here, say, okay, this is not part of it. Let's see, we got x to the 4th minus 14x cubed plus 102x squared minus 350x plus 533. This is not in your book, by the way. This is something I came up with. This has no real zeros at all, neither positive nor negative real zeros. It has 4 non-real zeros. They are 3 plus or minus 2i and 4 plus or minus 5i. Okay, so there's an example of a polynomial with no real roots at all. All right. Okay, this is going to cover a bunch of problems, 57 through 63 odds. All right, I'm not going over these in detail because basically you're doing things that you've already done in the process of solving these problems. For example, 57, you're supposed to list all the possible rational zeros. All right, so you've got the possibilities for P over possibilities for Q, right? Remember those, and then possibilities for P over Q. But we've already gone through that process before. It's really pretty cut and dried. The same thing for 59. For 61 and 63, you use your calculator to graph the functions, or your computer, and based on the graph, find the rational zeros. All real solutions are rational. All right, so in other words, for example, on 61, you can pretty much see what the roots are just by looking at the decimals where the graph crosses the x-axis, and then you can come up with a fraction that equals those decimals. All right, so negative 0.33, that's negative a third, and then 0.5 is 1/2, and then 1 is 1. Okay, so those are your rational zeros. So that was 61 I just showed you. All right, the same thing applies to 63, and you write those as rational zeros. 63 looks like this. All right, so that's negative 1.5. That's the same as negative 3 over 2, 3/2, negative 3/2, and then 0.25 is 1/4 and 2. So that was 63. All right, so really pretty straightforward on those problems. Okay, 65. I don't want to skip over 65. I want to go into this in some detail. Now, the graphing is simple enough, and getting the rational root, here's our graph. All right, 1 1/4, 1.25, or 5/4. All right, 5/4. So if you do an analysis with Descartes' rule on this, we've got f of x is 16x to the 4th minus 24x cubed plus x squared minus 15x plus 25. So, according to Descartes' rule, we have 4 variations of signs here in f of x. So that means there are 4, 2, or 0 positive real roots. Now f of negative x has no variations of sign, so there are no negative real roots. So let's make a table for this. We'll have 3 columns for the 3 possibilities here, 3 combinations. Okay, so let's say we've got 4 positive real roots, so that takes care of the other 2 spaces there. Let's say we've got 2 positive real roots, and we're not going to have negative real roots. We already found that out, and so that must mean 2 non-real roots, and there may be 0 positive reals, and there would be 4 non-reals. Okay, so this turns out to be the case. 2 positive real roots, alright? And the zeros, we already found out was 5/4. That's only 1 positive real root, but it's a multiplicity of 2. 5/4 multiplicity 2, alright? And the other 2 non-real roots are negative 1/2 plus square root of 3 over 2i and negative 1/2 minus square root of 3 over 2i. Alright? So those are your 3 roots, or rather your 4 roots. The positive real root has multiplicity 2, as we said, and so that's counted twice in Descartes' rule. So you've got multiplicity 2 here, so that counts for 2 in Descartes' rule. Alright? Okay, I just wanted to bring that out. '67. For the following exercises, construct a polynomial function of least degree possible using the given information. So we have real roots negative 1 and 1. And multiplicities are 2 and 1, so negative 1 has a multiplicity 2, and 1 has multiplicity 1. Alright. Also, they say that 2 f of 2 in other words, you look at this as a coordinate pair. Alright, so x is 2, y equals f of 2. Alright, they're going to tell you what f of 2 is. That's 4. F of 2 is 4. So we have a coordinate on this graph of 2, 4. Alright, so how do you make this polynomial up? Well, you just use the given information. F of x is going to equal some non-zero constant a, put that out in front, And then you take into account this is a root or a 0 of multiplicity 2. So that would mean that one of the factors in this polynomial must be x plus 1, because when x is -1, plug it in there, -1 plus 1 is 0, so you get a 0 that way. All right. Now it's a multiplicity of 2, so it's going to be x plus 1, or for short, x plus 1 quantity squared. All right. And then we have this root, a positive one, so that would mean that there's a factor x minus 1. Because if x equals 1, right there, 1 minus 1 is 0. All right, and then 0 times this and all of that is still going to be 0. Okay, it's multiplicity 1, so the power on there is 1. I just leave that blank. All right, so now what we do is we multiply these two together. Leave the a out in front for now. And you multiply that out, and then you multiply the result by that. Okay? So remember, do this first, order of operations. All right? And then you multiply by the last factor. What you should get is x cubed plus x squared minus x minus 1. All right. Well, how do we get the rest of this? It's not quite done. It's a lot more than we had before. Use this fact. When x equals 2, y equals 4. All right. So f of 2 equals 4, in other words. All right. So that means that plug in 2 for x's here, here, and here, those three places. Set that equal to 4. All right. So you've got a times 2 cubed plus 2 squared minus 2 minus 1. When x equals 2 again, y equals 4, or f of 2 equals 4. Oops, I was going to put a y there. Why? Because my mind was on the y. Alright, so actually that should be a 4. Alright, now it's easy to solve for a. Okay, so all of that equals 9, so 9a equals 4. And of course a equals 4/9. Okay, so therefore f of x is equal to 4/9 times the quantity x cubed plus x squared minus x minus 1. You could multiply the 4/9 all the way through, but you know, why bother with that? We could just leave it like this.